So thank you everybody for being here. Sorry for the inconvenience once again. The seminar of today will be given by Jean-Christophe Loiseau, and the title of his abstract is of his presentation is Dimensionality, Reduction, and System Identification of Dynamics. Let me briefly introduce Jean-Christophe. So he's an associate professor of applied mathematics and fluid dynamics at Métier Institute of Technology in Paris. His research can be divided into two broad categories. A large number of his activity has been devoted since 2010 towards a better understanding of transition to turbulence in three-dimensional flows by joint application of direct numerical simulations and linear model and non-model stability analysis. More recently, he focused on physics-informed machine learning techniques to identify reduced order models for complex systems for real-time control and estimation purposes. So thank you, Jean-Christophe, for accepting to give a seminar, and I leave you the stage. Please go ahead.
All right, thanks. So I'm gonna share my screen. All right, here it should be this one, I guess. All right, so I guess you can all see my screen normally.
Yes.
Yeah, that's the slide. All right. So thanks for the invite and this little surprise that we had with the first link. So I'll be giving my talk on dimensional reduction in system identification in fluid dynamics, and we'll use a particular flow all along, which is this one, which I'll get to in a second. Just while I give my presentation, you are welcome to ask questions. I have two screens, so I'll have one which has the chat. So I try to keep track of questions if there's any questions in the chat. And if it's relevant that I answer directly to the question, I will. Otherwise, we can keep it for the discussion afterward. So who am I very quickly? So as Francesco said, I'm the French equivalent of assistant professor in fluid mechanics and applied mathematics. I'm also a machine learning enthusiast, and I'm currently interested in efficient machine learning algorithm in terms of data and with some kind of guarantee of optimality, and for which we can somehow embed some kind of prior knowledge about the physics of the system we're studying. So in DinFluid, which is the lab I come from in Paris, we study essentially fluid mechanics from a numerical point of view. So fairly different fluid fields, from like this very simple canonical two-dimensional cylinder flow. I think this is Reynolds 100, and you see the vorticity. It has this nice periodic vortex shedding that is happening, all the way to strongly compressible and turbulent flows. So this is the turbulent fluctuations in a rocket engine nozzle that you see. It's fully three-dimensional. I don't remember how many million grid points. Pretty big calculation where you can see turbulence, shock waves, interactions between shock waves, turbulence, boundary layers, extremely complicated things. And the fluid that we'll look for today, which is this annular geometry. So this is a heat exchanger, basically. So it's a thermosyphon. It's called a thermosyphon. Well, we heat from below and we cool from the top. And what you see is the temperature field over time. And you see that there are some convection cells that sets in, and they start to rotate clockwise or anti-clockwise, and they switches. And this is the dynamics we'll look at today. So what do I mean when I say machine learning for physical system, and why do we use machine learning in these kind of setup? So our general setup will pretty much be the following one. So we start from a high dimensional system. It could be either data from simulations, or it could be an experiment. Through some kind of dimensionality reduction techniques, we want to represent these dynamics in a lower dimensional latent space. which is sufficiently low dimensional so that any calculation we can do is tractable. And then within this latent space, we'd like to identify, for instance, a dynamical model of the system in this particular low dimensional space using system identification techniques. And why do we want to do that? Because we basically want to close the loop, either for to use this reducer model for forecasting, for instance, in climate science, or feedback control in a lot of different applications. Or also we could only be interested in this dynamical model that we hope is easier to understand than the full Navier-Stokes equations, for instance. So that's kind of the general overview of what we'll be doing in this presentation and what I've been doing for the past 5 or 6 years now. So we're going to put a strong emphasis on low order models. I'm not going to present anything about deep neural networks for the moment. But models, basically, just so that we're all on the same page, model comes in a lot of different flavors, and Eugene Wiener proposed the following classification. So you have black box model. Let's start with white box model. So white box model are models for which you have input-output data, and you also actually know the model. The only thing you don't know maybe are the parameters of the model. So this is typically what we would do in high school when you have small electrical circuits. You have different input voltage, you measure the intensity, and you try to figure out what is the resistance, and you all know that's the Ohm's law. So you do know the law, you do have the input-output data, you just try to fit the parameter. So this is white box modeling. Then on the other end of the spectrum, we have black box modeling, and this is typically where you only have input-output data, you don't have anything else. And the archetype of a black box model would be a feed-forward deep neural network, where you have no prior knowledge about maybe your data has structure or whatsoever. You're not making any use of this. And then in between, we have gray box models. So gray box models are this part of the modeling, the model space, where you have input, output data, and you also have some kind of knowledge of what the model is or of its properties. You don't necessarily exactly know what the equations are, but for instance, in physics, quite often we do know that they need to satisfy some symmetries, or they need to have some invariants, which gives you partial knowledge of what the model can do, what property the model needs to have. And in machine learning, we call these inductive biases. So a simple example would be the following one, right? We're all familiar with this. So we start, for instance, from a Navier-Stokes simulations. We collect snapshots of the vorticity field over time. And then we perform some kind of dimensionality reduction technique to extract coherent structures from this data set, where once you project these dynamics onto these structures, then you get a simple representation of the system, which hopefully is tractable and amenable to a fairly simple model. So there are two kind of low order models we'll look at. We're going to look at low order deterministic models, but basically the aim is to identify an interpretable and physically consistent model, and that we'll get back to it, but basically we can use SINDy, where for the cylinder flow, if you define the amplitude and the phase of your vortex shading, basically you can somehow find the following system directly from your data, which is nothing but the normal form of a supercritical Hopf bifurcation. So it is physically consistent by design in this case. And as you can see, it's reproduced in blue. You have basically the evolution of the first and second POD modes over time. And in orange, you have this fairly simple model that reproduces exactly this evolution up to not much in precision, but pretty close. On the other end of the spectrum, we have low order probabilistic models. Now we try to identify a coarse grain model of the system. So this is pretty often used, for instance, in molecular dynamics, or when you look at protein foldings. Quite often you need to go through a coarse graining of the problem, otherwise it's not tractable. And you can do that using, for instance, clustering algorithms, and to transform your problem into a symbolic dynamics problem, where you have a discrete time probabilistic model, which is given by this vector of probabilities, and L, which we call the transition matrix of this Markov model, which basically states the probabilities of transitioning from one state to the other. So in this second framework, we kind of represent, where we'll see that we'll have to partition the state space and represent the dynamics, and no longer by using ODEs, but using what we call a finite state machine. But all of this is only possible if you have some kind of low-order modeling, low-order representation of your system. And so ideally, in fluid mechanics, we have very high dimensions, right? Usually it's fairly common to have a couple of grid points in your simulations, which is fairly high dimensional. And so ideally what we like to do with any kind of technique, that machine learning or any other technique, is to find a transformation of the data that we're going to call the encoder, that goes from the high dimensional space to the lower dimensional one, identify the dynamical equation in this low dimensional space, and then have the decoder, which is basically just the inverse of the encoder, that gives us the state of the system, for instance, one time step later. And so ideally, we like to learn this jointly, but it's extremely complicated from a mathematical point of view to solve such an optimization problem. So in practice, what we really do most of the time is we kind of learn the encoder decoder part separately from the dynamics. So that's what you would do, for instance, when you first compute a proper orthogonal decomposition representation of your system. And then within this POD space or PCF space, whatever you want to call it, then you learn the dynamics. So you separate the problem. And this is kind of what we're going to do, but not exactly. So our setup for today is the following one. So it's a two-dimensional flow, just for the sake of simplicity, which is governed by the incompressible Navier-Stokes equations. So we have two velocity component and a temperature field and a pressure field as well. It is governed by two different parameters, which are the Rayleigh number and the Prandtl number. So I'm not going to get into details. These are fairly standard physical parameters in buoyancy-driven flows. And what you can see is when you simulate the system, so this is done with NEC 5000, for instance, you get this evolution for the temperature field, right? So we heat from the two lower walls and we cool from the two upper ones. And so you have for a Rayleigh number sufficiently high, you have the onset of this convection cell that starts to oscillate, and from time to time, it's going to switch direction. So you're going to have flow reversal in this problem. And that's basically the dynamics we like to model using a fairly simple approach. So what we can do is, for instance, say, measure the flow rate through the cross-section of the system. And that's what it typically looks like, right? So you have the flow rate that is positive, negative, negative, positive, positive, negative, positive. And you have this kind of oscillations. And if you're familiar with even very basic dynamical system theory, this looks just like the Lorentz dynamics, chaotic dynamics. Well, we had some kind of random switching between clockwise and anti-clockwise rotation of the convection cell. And these dynamics, as we'll see, can be captured by a very low order model, which actually turns out to be the Lorentz system. So for those not familiar with the Lorentz system, so it's a system that was proposed in 1963 as a simplification of Navier-Stokes, basically, first performed by Saltzman. It had three different, it has a three-dimensional state vector, and it has different equations that you can relate to all the terms to different physical mechanisms like momentum diffusion, thermal diffusion, convection, and all that stuff. And you get these nice butterfly wings in the phase space, and it's a strange attractor. And so I could discuss about this, but it's not here. So how is the rest of the presentation going to go? So first, we're going to discuss a bit about the physical properties our brainstorm model needs to obey. And for that, we're going to analyze quickly the physics prior to perform any kind of modeling. Then we'll discuss very quickly how to obtain a good low-dimensional embedding. Once we have the low-dimensional representation of the system, then we'll see how we can use system identification to identify a set of equations that model these dynamics, and in particular, we'll discuss how to enforce physical constraints to make sure that the system we simulate is physically consistent. It respects all the physics we know it has to respect. So very quickly about the dynamics. So here's the temperature field, the radial velocity field, the azimuthal velocity field. So there's nothing much here to say. We have these clockwise, counterclockwise oscillation of the convection cells with some flow reversals. If we look at a bit more in terms of the statistics, so if we look at the empirical PDF of the flow rate, for instance, it's given here, and you can see that it is pretty much equally likely that the convection cell goes in the clockwise or counterclockwise rotation. If we look at the power spectral density of actually the time derivative of this one, just for the sake of stationarity of the signal, we see that we have a preferential time scale, which is a preferential frequency, which is associated with these oscillations you can see here. And then this is actually a continuous spectrum because, as we'll see, the system is chaotic, and so we have a continuous spectrum. We can kind of make the problem a bit easier by looking at what we call the telegraph signal. So we're going to start to use tools from symbolic dynamics. So the telegraph signal, for those of you not familiar with it, it's basically just the sign of this flow rate signal, right? So whenever the convection cell, say, turns in the clockwise direction, the telegraph signal will be 1, is -1. And this kind of simplifies a bit the problem because now we look at the influence of the switches on the dynamics. And here's the autocorrelation function of the flow rate and this telegraph signal. And what you can see is that the loss of correlation, so the correlation decay, is actually primarily dictated by the switches from clockwise to counterclockwise rather than by any kind of oscillation during these different phases. And this telegraph signal also allows us to compute extremely easily this kind of plot. So this is a timescale distribution of the system. So what you see is it's basically normalized here for the sake of simplicity. Most of the time, the system stays in, say, the clockwise or counterclockwise rotation for a given period of time, which is approximately, let's say, 0.125, something like that. Then let's say this is 50% of the time, then 25% of the time it will actually perform 2 oscillations before the flow reversal happens. Another half of this, 12.5%, will perform 3 oscillations, so on and so forth. And so this is kind of an exponential decay. So it's getting less and less likely that the system performs more than just a handful of oscillations before the flow reversal happens. This is, for instance, a highly statistically unlikely event where it performs a really large number of oscillations. Most of the time, it will either be 1 or 2 oscillations before it switches. So these are kind of the dynamics we want our reducer model to reproduce. And these are kind of the statistics we want the reducer model to reproduce, like the correlation decay, how long the system is correlated. All right, so let's move on to the dimensional reduction part. So I'm going to reformulate DMD slightly differently than what you may be familiar with. So for those of you who are not familiar at all with DMD, so DMD basically takes as input a discrete time system, could be nonlinear system, right? So xk equals f of xk. And DMD basically aims to find a low rank linear operator A that approximate this nonlinear function f of x as best as possible in the least square sense, under some constraint about the rank of this operator. And this was introduced initially by Peter Schmidt 10 years ago now, and Clancy Rowley. But as you'll see, it turns out that the algorithm they provide only give a suboptimal solution to this problem. And if you recast this problem into what we call reduced rank regressions, which have been studied by Alan Eisenman as early as the 1970s, 1960s actually, we'll see that we can actually derive a closed form solution of the optimal solution to the DMD problem. So we can reformulate this problem as a matrix problem, right? So if we gather all our different x1, x2, x3, x4 into this big X matrix, and Y is the one step ahead version of this time series, then we have this matrix form of the optimization problem. If you forget about the rank constraint for a moment, then the solution is basically just the least square solution, right? The unconstrained least square solution, where you have the inverse of the variance covariance matrix of X times the cross covariance matrix of Y and X. Problem is, this is usually hill-post because we have typically X and Y would be, for instance, 1 million rows by a few thousand columns. So it's really hard to converge these statistical objects, which are the empirical variance covariance matrices. And so usually this inverse is ill-posed, and you need to use the pseudo-inverse, for instance. But we can actually compute the, and so what for instance, Jonathan Chu or Peter were doing is basically they approximated the low rank factorization of this matrix, which is not the same thing as finding the low rank solution of the problem. So introducing the low rank factorization of this matrix, we don't know. So it's a low rank matrix, so we can write it as a product of two low rank matrices. Right? This minimization problem, we can basically recast it as follows, while we have a constraint on the rank of P and Q. And without loss of generality, we can say that P is an orthogonal matrix. So from a technical point of view, P is a basis for the column span of A. So P is basically a basis, it's basically going to span the same subspace as what we classically call DMD modes would do. And Q is a basis for the row span of A. And so this is, in general, what we'll call, for instance, the adjoint eigenmodes, the adjoint DMD modes. And in general, P and Q are different. So this is a fairly complex problem to solve directly. It is a non-convex problem because of this rank constraint. But if I'm going to skip over the details, but basically you can recast this problem just like for POD, you can actually recast it as this straight maximization problem, where this matrix here is a symmetric positive definite matrix. And the solution to this DMD problem, DMD optimization problem, is actually given by the leading eigenvectors of this SPD matrix for the P vectors. And then once you have P, you can recover Q using this equation. So we do have a paper with Steve Branton, colleague of mine, where we're currently wrapping up the paper where we explain all the details about this optimal solution. So why we use DMD and not, for instance, POD? The reason is because once you have P and Q, you can easily factorize A using its eigenvalue decomposition, right? This will be just straightforward to do, even though A is a large matrix, crazy large matrix. From the moment it's low rank, this is extremely easy to do. And now we can reinterpret DMD in this framework I've presented initially, where we start from the high dimensional space. Our encoder matrix is this psi H matrix, which is sort of the adjoint DMD mode that's going to project us into a low dimensional space. In this low dimensional space, our dynamics are approximated as being linear, and more the matrix of the dynamics is diagonal. And then we move one step forward in time, and then we can map back to the original space using the psi matrix, the decoder matrix, which is nothing but the DMD modes, what we classically call the DMD modes. And that gives us the solution one time step ahead of our system. So DMD can really be understood as an optimal combination of the linear autoencoder for dimensional reduction and the linear time invariant model for the latent space, at least for the one step ahead dynamics. that is optimal in the L2 sense, in the least square sense. So you're not going to have a better model than that, assuming linear dimensional reduction and linear dynamics, right? And so if you were to use POD, for instance, for the reduction part, then you would directly underperform compared to DMD for this task of projecting, predicting one step ahead in the future, the solution of the problem. One really nice thing also about the solution, solution is that in the classical DMD problem, there was a major problem that was how many modes do I need? How do I choose the mode I need for my expansion and all that stuff? Here, because this is based on the matrix which is symmetric, positive, definite, it is just like POD, right? You can look at the eigenspectrum of this matrix, look how the eigenvalues decay as a function of the rank, and then decide where you truncate and have some kind of measure of how much energy you discard. It's not exactly the energy, but that's kind of the idea. So in our problem, we have a sampling period for the DMD problem, which is approximately 1/20 of this fundamental period that we've seen, which is the period of oscillation of the system. And for the sake of simplicity, we're going to fit separately a DMD model for the velocity and for the temperature field based on 20,000 snapshots that we've collected in the problem. And here is the eigenspectrum of this symmetric positive definite matrix. And what you can see is that for the velocity field, you have a rank 1 model. That's the only thing you need for the velocity field. And you have a rank 2 model for the temperature field, right? So even though our simulation initially had something, so how to choose P, to quickly answer to Yun. P are given by the eigenvectors of this matrix. And so the rank of P is given by how fast the eigenvalues of this matrix decay. And that's what's presented in this figure, for instance. So even though our simulation initially had, I don't remember in this case, something like 200,000 grid points or degrees of freedom to simulate a problem, from a dynamical point of view for the one step ahead prediction problem, the system really only has just 3 degrees of freedom. All the rest is not predictable using a linear model. Right, so this is really important to grasp. What do these modes look like? So this is for the velocity. So you can see that for the velocity, it is pretty much invariant in the azimuthal direction. And if I were to extract the slice here, it would kind of look like a Hagen-Poiseuille, a Poiseuille velocity profile, kind of like a parabolic velocity profile. And then for the temperature, we have these 2 modes, right? So the first DMD mode captures basically the left-right temperature difference, while the second DMD mode captures the up and down temperature difference. Right? And this is really similar to what the Lorentz system, how the Lorentz system is built, right? For the velocity for the Lorentz system, you use just 1 mode for the temperature, for the velocity, which is sort of the convection cell, the eigenmode of the linearized Rayleigh-Bénard operator. And then the temperature field, you have 2 temperature modes that you need to take into account. So how does the latent space look like? So what if I were to project my 20,000 snapshots on the span of these 3 modes? This is what it looks like. So it looks like just the Lorentz system, right? So x of t is the projection for the velocity field, and y of t is the projection for the left-right temperature difference, and z of t is for the vertical temperature difference. Right? And so we get these kind of phase plots where, once again, if you're familiar with Lorentz, this is just like the Lorentz system, right? If you're really familiar with the whole thermosyphon, it shouldn't come as a surprise, but this is still a pretty nice application, I believe. All right, so from now on, we're going to work in this latent space. We're going to try to model how we go from one point to the other in this latent space using different techniques. So the first one is, before doing any kind of system identification per se, we're going to try to quantify a bit the statistics of this chaotic system to sort of see basically what we really want to see is how far in time can I predict statistically? Because then when we're going to identify a system, there's no point in trying to optimize the system to predict on a time horizon which is larger than, say, for instance, like a few Lyapunov timescales for this chaotic system. So the approach we use is now pretty standard, I believe. It was proposed in 2014 by Erika Kaiser and her co-workers. It's called the cluster-based reducer modeling, so it's called CHROME. What the idea is basically we're going to use clustering to have a coarse grain of the state space. So we're going to partition the state space. So this is kind of similar to the Ulam-Galerkin projection, if you're kind of familiar with this. And this will enable us to get a linear model for the probability density function, how it evolves from one partition to the other, and have access to some statistical properties of the system. And so to do that, to go from the continuous to this kind of symbolic dynamics, we use k-means, which is a fairly standard off-the-shelf machine learning algorithm, and then just simple maximum likelihood estimation to get the transition probabilities from, say, this cluster to this one. So very quickly, how does k-means works if you're not familiar with it? So given a set of n observations, so that's basically all our small points here, the idea is to partition them into k different sets, right? C1, k different clusters, partitions, C1 to Ck. And how do we do that? Well, there's a lot of different algorithms for that. The simplest one is called the k-means, and it basically aims at minimizing what we call the within cluster sum of squares. So it basically chooses some kind of centroid for this cluster, for instance, and then it measures the variance of all the points assigned to this cluster. We do the same thing with this one, and then there's this kind of optimization where we reassign the points such that we have approximately well-behaved clustering, well-behaved partition of the system. So it's really pretty standard algorithm. So if we do it for our problem, that's the kind of partitioning we get. So all the black dots are the clusters of the different partitions, right? So this is kind of the average, the conditional average of the state of the system, condition on when it's in this light green region somehow. And so now instead of looking at a continuous evolution, we're going to see how we transition from one cluster to the other. And so in this case, I've chosen 11 clusters, I think. There's different heuristic to choose the number of clusters. In this particular case, I think the optimal choice is something like 13 or 14, but it made a figure which was not as nice, right? The color bar was terrible, personal point of view. All right, so once you have this clustering, then you can basically look at the symbolic dynamics of the system, right? So you can have this continuous evolution, right, for the amplitude of the velocity field, for instance, gets transformed into this discrete evolution on an alphabet of symbols, which are associated to the different clusters. And this symbolic dynamics, you can easily model it using a Markov chain, right, which is a fairly simple probabilistic model. How do we do that? Well, we just use standard maximum likelihood estimation, which is I'm going to look whenever I'm in cluster 1 at the next time step in which cluster do I end, and then use kind of normalized by the number of transition you have. Right? So it's a pretty simple approach, and you get this kind of model where L is called the transition matrix, and its entries basically encode the probability. For instance, here the 1-1 entry encodes the probability that if you're in cluster 1, one time step later, how likely it is that you'll still be in cluster 1. And what you can see is when you're in cluster 1, which is let's say probably this one, maybe, there's a probability that you end up in cluster 2 one time step later, so on and so forth. And if you're familiar with these kind of transition matrices, what you can see are two, I'll get back to this question later, Chris, are two kind of mega clusters which corresponds basically to the clockwise and counterclockwise directions of rotation. And then this very last cluster here, C11, basically is this cluster here, which allows the system to transition from one mega cluster to the other mega cluster. And so you can kind of get this high level representation of the system in terms of I have a number of clusters associated to the anti-clockwise rotation of the system. Even though here it rotates in the clockwise, this is a really poor choice of representation. And here a number of clusters associated to the clockwise rotation, and this one which enables the system to switch from one state to the other. But that's not really the interesting part. The really interesting part is actually the eigenspectrum of this transition matrix. So this is called a stochastic matrix, which its eigenspectrum actually encodes the diffusion of the probability density function. So basically, the different eigenvalues encode how fast the system relaxes to its invariant measure, so to its mean statistically steady state, basically. Because this is a positive matrix and it is a stochastic matrix, the Perron-Frobenius theorem basically states that it has one eigenvalue which is exactly equal to 1, and the eigenvector associated to it basically gives the long time average or the ensemble average of the probability density distribution. That's really not of interest for us. What's really of interest is how fast this PDF diffuses. So basically how fast the system forgets its initial condition. And this is actually given by the ratio of the second eigenvalue to the first one, the modulus of these eigenvalues. And so the larger this ratio is, well, the smaller this ratio is, my bad, this should be the smaller, the faster the PDF converts to its invariant measure, right? And so for our problem, we can look at how lambda to the k, so after k time step, how fast it goes to 0 for different numbers of clusters. And here you can see that basically after tau, a time scale equals to tau, which is this one oscillation, it goes to 0.5. And that's, in a nutshell, that's not exactly what it means, but in a nutshell, what you should understand, how you should interpret it is that after one oscillation, I have a 50% chance of continuing on the same part of the attractor or moving to the other part. And after just a handful, like 3 or 4 times, the characteristic timescale it takes me to perform one oscillation around the wing, then this ratio goes to 0, pretty close to 0. So it means I might as well just guess the mean value rather than any other value. Statistically, I will be more, I'll have a smaller error. So from a system identification point of view, this kind of plot really is important for us because it tells us there is no point in trying to find a reducer model that predicts accurately the state of the system more than, say, 5 characteristic timescale in the future, because on average, I might just as well predict the mean state and I'll have a smaller statistical error. So let's move on now to the identification part. So what we're going to use is this sparse identification of nonlinear dynamics. So it's an algorithm that was proposed 5 years ago by Steve Branton. Well, the idea is we want to identify a lower model of the system. And why do we want to do that? It's because in SINDy, you can identify a set of ODEs, right? Inherently interpretable ODEs, which are basically the language of physics. And because it's a simple set of ODEs, then hopefully you can have really fast evaluation for forecasting purposes, for instance. How do we do that? Well, that's basically just least squares in disguise, right? It's sparse least squares with constraint, possibly, but it's really, the methodology is really similar to least squares. So as I was saying, this was proposed by Steve Branton in 2015 in PNIS, relies on the dictionary of predefined function and sparsity promoting regression. And it's a framework we've been working on for the past 5 years with Steve, extending it for control, with constraints, which is what I'm going to present. It's been associated, related also to the Koopman operator and a lot of different things. So how does it work? If we take the Lorentz system, for instance, What we're going to do is we're going to specify what we call a dictionary of functions, right? So it could be for the Lorentz system, for instance. It kind of makes sense to say, I'm going to look in my f of x as the combination of different monomials in x, y, and z. So it could be like all the polynomials up to degree 5 in my state variable. And so we collect x of t, we collect x dot, y dot, and z dot as well, or we estimate it from the time series of x, y, z in some way. And then basically sparse regression, what it's going to do is it's going to try to find the vector of coefficient of these different candidate function, which has the smallest number of elements, and yet reproduce correctly the left-hand side vector. So for the Lorentz system, typically what you can see if we do it for the Lorentz system is that the first set, the first vector has only a cardinality of 2, and the function he picks from this library of functions are indeed x and y, which is what we have in our original system. And so once you have identified the system, then you can simulate it, and hopefully, if you do things properly, it should match pretty nicely the original system. So how do we formulate it from a mathematical point of view is the following. So given our dictionary of functions, what we really want to do is minimize the cardinality of this vector of coefficient. So the cardinality or the L0 norm is basically just the number of non-zero elements subject to a data fidelity term, right? We want this approximation of x dot to be as close to the true x dot as possible, although we allow some kind of, to have a bit of noise. The problem with this is a combinatorial problem, right? So you would need to test, because this is the L0 norm or the cardinality, you would need to test every possible combination of xi to solve the problem. For the problem we're looking at right now, it's not so much a problem, but it becomes rapidly intractable when you apply it to a system which has even just say like 10 degrees of freedom. And we do need convex relaxation or Green algorithms to approximately solve this problem. So in this case, the nonlinear Navier-Stokes, the Navier-Stokes equations are nonlinear PDEs with quadratic nonlinearity. So it kind of makes sense from a practical point of view to choose a dictionary that has only up to quadratic functions, at least as a starting point. And so if we do so, then the unknown model that we like to identify basically takes this form, right? So we have x dot is basically a linear combination of all these functions, same for y and same for z dot. So we have something like 30 or 35 different coefficients we need to identify from our data. The thing is, we actually have some kind of knowledge about the system, right? So if we look at the phase space, the phase plot, we see some kind of, that the system appears to be equivariant with respect to a transformation that transforms x to negative x and y to negative y, right? So if I flip in the vertical direction and the horizontal direction, I get back the exact same figure. And this mathematically is, can be represented as follows, where we have gamma, which is the matrix representation of this flip operator here that goes from x, y, z to negative x, negative y, z. And so for our reducer model to be equivariant, it needs to satisfy this equation. And this basically puts a massive constraint on the pool of functions you can have. And if you enforce directly this equivariance of the system, then you go from this 30-term model then to just 14 of them. So a massive reduction just by adding this equivariance constraint. But we have other constraints that we know for the system to make the identification even easier. In this case, we know that the system is called dissipative. Right? So for those of you not familiar with a dissipative dynamical system, that's basically the Lorentz system here. You start from all these blue dots are different initial conditions, and basically they basically converge extremely rapidly to the attractor. That's not exactly what the dissipative system is, but that's kind of give you the idea. It's like you sort of converge to a non-periodic solution, kind of. So we know that the system is dissipative, and mathematically it is written for the whole phase space. And so it's written by this, the divergence of this f of x has to be negative for the whole phase space. Given our model here, we can write the divergence of f of x and force it to be negative. It gives us a set of constraints that forces us to identify all three equations simultaneously, right? We cannot identify one and then the others. They are coupled by this constraint. And finally, we know that the Navier-Stokes equations are the quadratic term basically somehow preserves the energy, right? It doesn't destroy energy, just scatters it among the different length scales. And so if we start from our state equation, our dynamical equation, while Q of x here is the quadratic term, and we define our energy, then the energy equation needs to be given just by this expression here. So x transpose times Q of x needs to be 0 for Q of x to preserve energy. And so in our problem, it means that our energy equation needs to take the following form, and it gives us additional constraints actually on these coefficients, which are associated to this quadratic term. So finally, we can formulate our optimization problem, right? So we can minimize, we aim at minimizing the cardinality of this vector of coefficients. So these are the coefficients of our equations, subject to that fidelity term, which basically tells us how good our approximation of x dot is, under some constraints, which are here to encode our prior knowledge about the physics of the system, right? So the equivariance property, the dissipative property, and the energy preserving property of the quadratic nonlinear term. This is still a combinatorial problem. So you can use convex relaxation. For instance, it could be here we use Tikhonov regularization, so we regularize the L2 norm. It's not per se a sparse promoting heuristic, but in this case, it just works the same. It doesn't really matter what this regularization turned out. This kind of came as a surprise. So we can solve this problem. So let's move on now to the last part. So we have our data sets, which by the way, for those of you interested, will somehow be available online shortly as soon as I find a way to store it. Has approximately 500 periods of oscillations of the convection cells. We're going to partition it into training and testing. This is pretty standard. The whole optimization problem is implemented using Civic's OPT, the fairly standard optimization library for convex optimization. And now the model selection, because we have this lambda parameters that we somehow need to tune, is have a model parameterized by this lambda. And so how do we select it? Well, we've decided on order statistics of the true system. So what this means is for every lambda, we're going to identify a system, a reduced order model. We're going to simulate it. We're going to basically extract the variance covariance matrix of the state vector. And we're going to compare this variance covariance matrix of the simulated system to the one from we got from our training data set. And to do that, we use the Kullback-Leibler divergence, which is basically just a measure of how different two variance covariance matrices are. So what you can see is that the unconstrained models, right? So pure least squares, no constraint on the sparsity, and no prior knowledge about the equivariance and dissipative nature of the system whatsoever. This is in log scale here. You can see that they perform extremely badly, right? The similarity between the variance covariance matrices is extremely bad. From the moment you add the constraints, so there's not all the plots here. This one has absolutely all the constraints, and you can see that the sort of the optimal model is this one for this particular choice of lambda. This is the one that has the smallest Kullback-Leibler divergence. I really should have updated this figure because you can then also look at, all right, what if I have just the first constraint or the second constraint or the third constraint? And what you would see is that the most important constraint is, in this case, turns out to be the dissipative nature of the system. That's really the one that that is the most important in this setup. So let's look at what this system looks like. So it looks like just like the Lorentz system, right? So you have this fairly nice structure. We do have a constant term here in the Z equation, which does not exist in the Lorentz, but this is just basically because we've expressed everything in terms of the mean flow rather than the base flow. So we can basically shift the origin to recover a Lorentz-like model. And by design, it satisfies absolutely all the constraints. And what you can see here is the gray lines are the trajectory recorded from DNS and projected onto the span of the DMD modes. And the blue dots are the prediction of the reducer model, right? So it performs fairly nicely, I believe. And the nice thing is now we can actually interpret every single one of these terms in terms of a physical mechanism like this would want. This in the X equation, this negative X would be the momentum diffusion, while this one would be the buoyancy force, for instance. So you can really look at the different terms. How does it perform in terms of simulations? So once again, in gray, you have the time series recorded from DNS, and in black, you have the simulation of the model, and you can see that for this particular initial condition, we do capture correctly the system all the way up to when it switches, which corresponds approximately to this time scale that was given by this probabilistic model. So there's no point in trying to have a model which is more accurate than basically this time scale. So this is all consistent, and you can see that all the time series looks pretty similar in the eyeball norm. And we can quantify this a bit more using, once again, the telegraph signal of the system. And you can see that the autocorrelation function is almost a perfect fit, right? So the model in black and the DNS in gray, we have the exact same cutoff of the correlation decay. It's a two-part function. The timescale distribution is pretty similar. It seems like in the model we had some kind of underestimate of the two oscillation state of the system, but this could also be that we just don't have any enough measurements, enough snapshots in the DNS to properly converge these statistics. That's a possibility because the reducer model, remember the DNS, we have 500 periods of oscillation. In the reducer model, we've simulated 1 million of them in just a couple seconds. So it could be either way. Either the model kind of miss small part of what's happening here, or it's just our original statistics which are not converged. We can look a bit more quantitatively the marginal probabilities of the different state variables, and you can see that there's an overall good agreement. Not so much when X and Y's are really close to zero, but that's once again correspond to the situation where the convection cell is about to switch, right? So it has, we have very few instances of these snapshots in our data set. So it could be also just an under estimation of the of this empirical PDF. Or we're missing, or this could be related to physical mechanism that we cannot capture with just these three DMD modes. And so finally, we can use it for forecasting. So as you may know, the Lorentz model, there's some part of phase space where forecasting is extremely complicated. So this is one such situation where basically the starting point is the system is about to switch and our forecast just predicts that it switches in the wrong direction. Other part of the phase space are much easier to predict, and you can predict for 2, 3, 4, or 5 characteristic timescales fairly easily. So how does it look in the eyeball norm if we put everything together? So on the left part, this is the DNS, right? So the temperature field, and this is the reserve model. So this is, we project the initial condition. The initial condition is the same for both simulations. We project it onto the span of our DMD modes. Initialize our system for ODEs, simulate it, and then we reconstruct with the decoding matrix basically to get the state. And you can see that, all right, the video just restarted, I guess. Let's just restart the video. you can see that it kind of follows nicely for like a few oscillations. And then because the system is chaotic, once one switches, it becomes, it's no longer synchronized. But even though we have only 3 degrees of freedom, just 3 modes to reconstruct the whole thing, you can see that in the eyeball norm, it's doing an okay job, right? Reasonably good job, given that this one has something like 200,000 degrees of freedom. This one has only 3 degrees of freedom. So I'm going to cut this long story short. I have no idea if I exploded the time, so I'm going to go pretty quickly. So just my random search and kind of cutting this long story short. Dimensionality reduction in dynamical systems is a pre-processing step that is required, at least in fluid dynamics, right? We start from a really high dimensional system, so we somehow need to project the data in a low dimensional space, but it has 2 competing objectives. The first one is we want to reduce the dimensionality of the problem as much as possible, but not too much, right? Otherwise, it's just pointless. But we want to reduce the dimensionality of the problem as much as possible. But ideally, since we want to model the dynamics, we also want to have the resulting latent space to somehow be well suited for modeling these dynamics, right? If this Lorentz-like attractor was like all twisted, it would be extremely complicated to find a set of equations. So while goal number 1 can easily be formalized mathematically, right? It's just you minimize some kind of loss function, some kind of L2 norm of the difference, for instance, if you look at the least square sense. The second goal is a bit more abstract, right? What does it mean mathematically for a coordinate system to be well suited for modeling dynamics? This is a bit more abstract. What I can say is, given if you have full state data or even just partial state data, then you can use Tachan's embedding somehow to get more data. My personal experience suggests that DMD-like techniques are pretty well suited because, well, first of all, they rely on extremely highly efficient numerical linear algebra techniques. And the low dimensional space is interpretable in the sense that we do get spatio-temporal coherent structures that we know how to interpret from a physical point of view. And also, as I've shown you, if you do things properly, if you use the actual optimal solution of the DMD problem, then you have the optimal solution, right? So you know that there's not going to be a better linear embedding than this one. The second thing is related to the Koopman operator. So if you're not familiar with it, it doesn't really matter. For those of you familiar with it, basically, you can understand DMD has some kind of a coordinate system where the dynamics are approximately linear, and it is somehow related to normal form theory, kind of where you kind of get the simplest representation of your system and easier to model. So that's my take. There's different point of views on this, but at least for simulating dynamics and not just statistics, for dynamical modeling, DMD is the tool you should use. You should not use POD, for instance, which primarily aims at approximating the statistics and not the dynamics. Then this is more for people interested in machine learning. So learning the input-output map is not the same thing as learning the physics. And recently there's been a number of papers illustrating this, where basically you can have a model, say a neural network, that gets the input-output properties of your system extremely accurately. But then when you start to tweak at the properties of this neural net, for instance, you realize that it obeys absolutely no properties about the physics, right? So it maybe doesn't conserve energy, or it has absolutely no invariance or whatsoever. And so learning the input-output map, which is what people in machine learning are interested in, is not the same thing as learning the physics. And even on this fairly simple example, an algorithm as simple as linear regression completely fails. It was not presented in these slides, but we did the same thing with a fairly simple recurrent neural network. Doesn't work either out of the box. And you really need to explicitly enforce any kind of prior physical knowledge you have of the system, because not only would this usually reduce the your hypothesis space. So it will lead to easier training, but it will also lead to orders of magnitude more accurate models and models for which you are sure they preserve or respect any kind of physics you know they have to respect. So how to scale things up? This was a fairly simple problem. So there's been some work recently about equivariant autoencoders, where these are autoencoders from machine learning, where you somehow have this equivariance property to encode, for instance, spatial symmetries in the system, so that your dimensional reduction algorithm satisfies these spatial symmetries. So in our case, that would be the left-right symmetry, for instance, of the temperature field. You can also use differential programming to treat a neural network as a regular function f of x and apply differential operators to it, like computing its divergence with respect to the state, and then add this in your loss function when you train the whole neural net to make it sure that the divergence is negative, for instance, for a dissipative dynamical system. And very recently, there's been some work from physicists about trying to encode physical knowledge in the very architecture of the neural network. So that's, for instance, what we call Lagrangian neural networks, which have been shown to basically respect the fact that, for instance, for the double pendulum, we have the Lagrangian or the Hamiltonian. It's been extended for Hamiltonian system, for instance, where the network itself, the prediction is sure to be the solution of the Hamiltonian problem because the architecture make it so that it has to be the solution of such a problem. So thank you for your attention, and I'll be happy to take any questions.
So thank you, Jean-Christophe, for the presentation. I would say whoever has questions can open his or her mic and directly ask a question. If there are too many, then we start moderating it via the chat.
Hi, I have a question. May I proceed?
Yeah. Go ahead.
So my question is, I've seen all these things that you're saying about dynamical systems, and at some point you propose that you will be scaling up to more complex flows and turbulent flows and things like that. And my question is, I mean, I have seen results from this methodology that go up to Reynolds number of 100 and things like that. So my question is, what's the bottleneck to scale up these techniques?
All right, so that's an excellent question. So I don't think a naive application of this technique to turbulence would work right away. Essentially, this is some stuff we've been doing with Steve and Jared recently. We started when we were all at IPAM last year, where we've extended SINDy to identify stochastic systems, right? So stochastic dynamics, where one of the assumption is, provided you have some kind of scale separation between the fundamental frequency of your system and the turbulence dynamics. So for instance, if you take a turbulent vortex shedding, usually you have a really relatively nice peak in the power spectral density, and then you have all the turbulence, which might be 1 decade higher frequency. In this case, stochastic formulation of SINDy might work, and it does work. We do have an ongoing work with Giorgio Riga from Imperial College on this. In the more general case, you will essentially be limited by a few things. First things first, in the, and I think this is true even for autoencoders, if we get back to the DMD, at some point you have these variance covariance matrices that you somehow need to converge. So if you have very few data of a really highly turbulent flows, I think this is a recipe for disaster, to be fairly honest. So it really comes down to how much data you can have and what it is exactly you want to try to predict. If you want to try to predict, for instance, just the drag evolution over time, might be much easier than trying to predict the velocity field.
Thank you very much.
Does that partially answer your question, Petrus?
No, thank you very much.
So Chris had a question on the chat during the presentation. So yeah, if you know that the data lives a priori on a given manifold, obviously you can use a particular metric associated to this manifold, or you can, I think there are extensions of k-means on manifolds, like on Riemannian manifolds or stuff like that. So I'm not 100% sure, but there's probably some way to encode that prior knowledge about the fact that data lives on a particular manifold and encode this in the norm you use for the k-means. That's very possible.
So Jean-Christophe, I think you have a question also from Yongyun. So please, Yongyun, ask your question directly without.
Thank you. Thank you for the nice talk. One quick question. So you said actually at some point actually you would use DMD instead of POD, but the DMD bases are not orthogonals. I mean, if you have like the 3 degree of freedom like this, then you can maybe DMD would be better because it contains the dynamics. But if you have a like say like 1,000 degree of freedom, then I don't know how you say. Yeah. What is your opinion about that?
So that's related actually to the properties of this. It's actually extent that I'm on this slide. It's actually related to the very, I think I do have one slide at the very end. Yeah, this one. All right. Yeah. So if you think in terms of principal component analysis, POD, like Carhoon, Loiseau decomposition, whatever you want to call it, it can be formulated as this eigenvalue, generalized eigenvalue problem, where P and Q, well, X and Y are the same and P and Q are the same, right? These are covariance matrices, so it's symmetric positive definite, so P form an orthonormal basis. For DMD, what we have shown, and we're able to submit the paper actually, is it is kind of related to PCA, but we now have this other generalized eigenvalue problem, where this matrix is still a positive definite, and P will form an orthogonal basis for the DMD subspace.
Okay.
So you can always project onto this orthogonal subspace, just like you would do with POD.
But I thought this is also
which
what
is not the case of what Peter.
Yeah. It's a different. I
understand not exactly what Peter was doing.
Yeah. But the Peter project onto. Okay, that's fine. Sorry.
So what Peter is doing, where it is.
Peter project first on POD and then POD.
If I start from here.
Yeah.
Yeah, but he projects on the POD of X.
Yeah.
Right, of the input to this problem.
Yeah.
Well, here, if you look at the properties of the solution, the P vectors here, they're not exactly the POD modes. They're slightly different than the POD mode. They're closely related to canonical correlation analysis. So you get these two subspace, P and Q, right? Q is a subspace basically for X, and P is a subspace for Y, and these two subspace are somehow maximally correlated with one another. So when you use this formulation of DMD, you're 100% sure that whatever low rank projection you use, the two subspaces of the input and the output are maximally correlated, linearly correlated at least. And so it has better properties than Peter's solution. If you want to put Peter's solution in this optimization problem and look at the result in terms of the loss function, it could be 3 to 10 times not as good.
I mean, sorry for taking so long, but if I understand correctly, the Peter's method is basically use POD modes actually to generate the basis, and then which is actually based on maximum in terms of the energy. But this one is based on the input-output correlation. Is that correct?
Yeah, that's one thing. The other thing also is one limitation of Peter's algorithm is that assume you have a linear system and A is truly a low rank matrix, right? And you only have X and Y. You try to recover A, sorry. If you design X to be the identity matrix, for instance, and then you apply Peter's algorithm, well, the low rank properties of X tells you nothing about the low rank properties of A, right? You can always design X to be the identity matrix. Well, in this technique, it's really, if X is a full rank matrix and it has nice property, you can show that the P modes are associated to the POD modes of Y, which is really, it's not the input that tells you that the system is low rank, it's the output. So there's, on top of what I've said about the optimal correlation between the input output, there's also this property that in the case of Peter, if you badly design your initial conditions, you're going to get a really bad estimate of A whatsoever.
Okay, so quick question. In this algorithm, how do you determine the rank of A? I mean, you don't know that actually in reality, the rank of A, right? So you choose a different value of R and then try that, so you get satisfactory answer. Is that?
So the nice thing is you get this this matrix here, right? You try to maximize its trace. This matrix is symmetric, positive, definite. So it's the sum of the eigenvalues, right?
Yeah.
And so just like in POD, right? In POD, you would compute all the eigenvalues of the covariance matrix, and then based on how fast they decay, you're going to truncate your decomposition. It's the exact same thing. So what I'm presenting here, for instance, in blue, these are the actual eigenvalues for the velocity model. And you can see that a rank 1 model captures 100% of this input-output predictability, but for the temperature, it has to be a rank 2 model. And then all the others are really close to 0.
Okay, thank you very much.
So that's how you would choose the rank of the model.
Yeah.
Exactly like POD, except that you would a slightly different matrix.
Okay. Yeah, thanks for that. Yeah.
Yeah, can I ask a question?
I think Bérangère had a question.
Yes, thank you.
Yep.
Thank you very much for the presentation. You speak about POD. How do you feel about spectral POD? Because I mean, it has been shown now that you can POD in time is not very different from DMD in some ways. So how would this? Have you thought about using spectral POD?
So I've started to look at spectral POD. One of the assumptions of spectral POD actually is related to time series analysis, and you somehow need to, for the results to really make sense, you somehow need this signal basically to be statistically stationary. For the power spectral density to make sense and all that stuff, which is not the case here, right? You have the variance clearly is not constant over time, so it's at best just weakly stationary and not strongly stationary, and it would possibly work. Although one of the problems I think with SPOD is, I mean, the two problems I have with SPODs, although I use it on a regular basis, don't get me wrong, I think it's a fantastic tool, but it's, first of all, once you have the SPOD modes as a function of frequency, it's not entirely clear how you project onto these modes, right? Whether you need some kind of, first of all, you need an oblique projection because the modes are no longer orthogonal. And you may need to have a space-time projection as well on a given window because these modes are statistically relevant on a given window of time. So it would, for a strongly turbulent flow, for instance, I guess it would probably be better than this, possibly. Although there are still these questions about like, how do you actually project onto the span of these modes, given that they are no longer orthogonal. I mean, they're orthogonal just per frequency, not among frequency. So I don't really know. I can't really answer your question.
Okay, thank you.
Any other question? Well, it seems that's not the case. So yeah. So well, then I thank you once again for your presentation, and I must say it was very, very interesting, and thank you for